So I remember last day we talked about thermometric properties, and different thermometers have different thermometric properties. For example, a simple liquid and gas thermometer, when you heat it, the liquid inside the mercury will expand. That's okay? And we said that we can take those values and convert them into temperature reading. That's it. Right? And then convert it into temperature reading. That's okay? Yeah. That's what we spent some time on. Right now, last day we also looked at the first scale called the thermodynamic scale that allows us to get temperatures in Kelvin. And we saw that we could use this nice little formula here, right, to help us get temperature in Kelvin. Right? Remember that to get temperature in Kelvin, we need pressure values. Right? We need pressure values and the unknown temperature and pressure at triple point. What's triple point again?
The point that where they have solid, liquid, and vapor.
Okay, temperature at which those three exist, right? At a particular pressure. What is the pressure?
611.
All right, yeah. Very good. Right?
611, right?
Yeah, 611.
Yeah.
Right. So the next thing you want to look at is something called the empirical scale. This scale allows us to get temperature, right? This scale allows us to get temperature in degrees Celsius. The first scale we did yesterday allows us to get temperature in Kelvin. This one is in degrees Celsius, right? Right? And we have to do all proof to get that formula and all written code, right? But let's just run through this fast. An empirical temperature scale uses a specific thermometric property of a thermometric substance, right? An empirical scale can be obtained for a mercury in glass thermometer by measuring the length of the column at ice point, at steam point, and then dividing the intervals, and then dividing between the two intervals 100 equal divisions. Remember that? So you find ice point, you find steam point, and then divide 100 times. Right? But what we'll do for resistance thermometer or different thermometer, right? We have to come up with this nice little formula, right? And I'm going to show you how to do it on the board. All right? So let's take a look at the proof of this formula, right? Actually, I can do it right here. But do it on the board. On the board. Catch up. Catch up. I'll put in the values, right? Sketch out. All right, so let's take a look at this here. So we're taking a mercury glass thermometer and we're taking some readings for how much the mercury expands, right? So we have mercury in here and we're going to place it in different temperatures. And we want to see how much the mercury will expand, right? So initially we have 0 and let's say 100 is about here. Okay, So take a thermometer, put a thermometer in pure melting ice, and the first reading we get, we call that reading L0. Right? Take it out, cool it down, put it into in steam above pure boiling water. And that value we get to call it L100. Right?
Calibrate anything.
Yeah, we can get a formula that can help us work for anything. Right? So technically, yes, trying to calibrate it. Right? Now let's go to unknown temperature. Let's call the unknown temperature theta. Place the thermometer in there, and the length that we get is L theta. Okay, so we have three lengths: L0, L theta, L100. All right. We need to develop a relationship that allows us to find what theta is. Right? So I want to take this thermometer and put it into unknown temperature, unknown substance. So your substance of unknown temperature and find that temperature. All right. So we need to find a way to develop a formula. Right? But watch how easy it is, right? You all remember how to find gradient? Right? So we're gonna try to find gradient, right? Change in y over change in x. All right, so watch this here. I'm gonna choose these 2 points, right? So I'm gonna choose this as y2, y1. So that's L theta minus L0 all over x minus x1. See that? Yep. Now I'm going to find the gradients again, right? Using different points. I'm going to use this point and this point. Okay, and this should be the same gradient, right? So I'm going to choose this as y2. And I'm going to choose this as y1. Right? And of course, this is x2. This is x1. Here's where I need your help. I want you now, remember the purpose of this whole thing is to find for theta. Right? I want you to develop a formula that can help me find theta. Do a little maths there. Pass on to watch. Online will get away. Okay, watch there. Right? Do your little thing, mix it up, change it up. I want you to get a formula for theta. Take theta, this up, get a formula.
I guess it's by
Right, we end up with.
I guess it's
Let's see. Right, and this is what we're going to use find all the time, right? So basically, let me do the long way. This is L theta minus L0 all over theta, right? Because theta minus 0 is theta. Here is L100 minus L0 is equal to 100. Our objective is to make theta the subject of the formula. So if you cross multiply, I'll get theta by L100 minus L0 is equal to L theta minus L0 by 100. So therefore, theta is L theta minus L0 all over L100 minus L0 by 100. Right? If you look at the handout of an error, what you can see. Right, there's a small error, right? I think I have an extra theta here. I think.
Yeah.
Right, so you'll fix it well. You didn't print it, but write this one down. That's what I made you do it, right? Right, so here's how it works, right? Let's try an example to show how it works. Right? Let's see how it works, right? So let's say the length in let's say the length at the boiling point is 50 centimeters, and the length that you got at the ice point was 20 centimeters. Right? All we need now is to get L theta, we can find theta. So let's say L theta was 30 degrees, sorry, 30 centimeters. See if we can find theta. Right? See if we can find theta. Try that quick. Right? Real simple. You just plug in these things in there. Right? And that's basically how the empirical formula works, right? This temperature will be in what again?
Celsius.
In Celsius, right? Right? All these values will be in Celsius. Next. It's like you'll come and reach out. All right. How much all I got? Right, Darian, thanks for coming to Darian and Jacob, thanks for coming to class, right? But basically, we just learning to find temperature, right? Using thermometric properties. Right, so theta is equal to L theta was what? 30. L0 was 20. L100 was 50. And pardon me?
Yeah, L. You're gonna take the data, get your own thing, you know.
Well, no, that's sorry. Where is it to be? All right. All right. Fix it. Sorry. Look, clean up, finish it. You realize that was missing. Right, so it could be 30 minus 20, 50 minus 20, right? So that will be how much?
33.5.
So that will be 10 over 30 by 100. How much? 33, right?
Yeah.
I thought you said 23.
Nah, I never said.
33.3 degrees Celsius. That's okay? So this is technically how calibration works. Okay with that? Try the one in your hand out there.
Wait, send a handout.
Try this one. Well, same thing in the handout. Right? The part one was the same thing I just did in class, right? Derived that. Right, part two now. We'll go that one. Anybody can tell me what the thermometric property is here? The last one was length. This thermometric property is what? Ohms. But not ohms. Ohms. Resistance, right?
Same thing.
No, it's not the same.
And omega is not.
Over the unit.
Right. Yeah. The rest of the you gotta have a good game. You got the streets. Deliveries.
Plus?
Yeah, jazz, you got it. 3,000 say. How much hours are it? 15 hours.
Oh yeah, plug it in, work it out. Let's go again after this. Finish. Work it out and make sure you get up.
I did.
And you get up.
Yeah.
You get up until you up.
did
You're working
that.
yourself.
I get 97.
How many boards? When you use the formula, right, and you're writing it, right, Adam.
See, I was wondering what the right R.
Correct, right, right? Yes, without passing, you should get that on the board. Let me make sure. That's wrong.
So do you want to get on somewhere?
Yeah, so it's wrong. Yeah, it's wrong.
Yeah.
Well, that was the one that was wrong. That's number 3 was the one that was wrong. So therefore, the boom at ice point. Ice point is 30. Steam point is 34.59. And sorry, I did the wrong thing now.
Well, you get 69.6.
41.58 is steam point. 41.58 and 34.59 on it boiling, right? When you multiply that by 100, you also say you got how much?
39.64. You don't believe me, though?
Nope. I'll check in the sure.
That's what your best thing.
Right, I have 59.964. Okay, from the top to like 40, so it's kind of close, I wonder why. Anyways, everybody okay with that? So that's basically what you do, right? Any questions online? Asirali, are you okay there? Soraya. Please send some answers, please, Soraya. Are you okay there, right? Let's try past people. You know? I'll go back and find out. What kind of video that you know? Pick up, quick now. Case you can't see it.
You said it.
What? Look at it.
Yes.
Yeah.
You tell you, no question. So, listen. Can you give me a rest of 5 o'clock? What? Till I want 5 o'clock.
I'll give that. It's enough.
Oh, yeah, Daya, can do so that please. If you can see it, you can zoom in, right? Online, please send out some answers, especially Soraya. Ask all you too, send some answers. And Barrage, Barrage. Barrage, you there? Yeah, all right, nice. Kind of put out. How you know which formula to use here? What they ask to find? Centigrade, right? So that's degrees Celsius.
What?
Centigrade. Temperature. Right? So once you see that, you know you're using degrees Celsius. Right? It is hardly ever use the word empirical, right? Sometimes they'll just tell you the what it's in degrees Celsius or use cent, right?
Alright.
But once you see anything with degrees Celsius, you know which formula you use. Ready? Got it? Please finish, right? All right, today, well, I like it. Something wood and cheese.
Yes, sir.
It's a physical one. Yeah, but physics that one, I'll check.
Now that we see that if it's not.
Sabe, tipo, memória que cachorro, vai estar falando para você que eu estava. Nah, I'm smart crap. You can still go language is something. Who? Iran? Nah. Next one. Crap, now. Shiva. What are you doing now? Fella. Where's Shiva? I think it's fella. I'm not getting trouble. It should be lower than.
So the answer 57.41.
I can work it out in 1 minute. And then trying to get it on the deep product cut out. Yeah. I don't know. Physics. That's the ones. I do have a strength booklet.
What book that?
Strength booklet. We only give any guy who's start them. I have a strength booklet. I don't have any possible. Or they can call it man again. I don't want to problem. Alright, so we have a constant volume gas thermometer, right? And was calibrated at ice points. Was calibrated at ice point and steam point. The temperature, the thermometer was used to measure the temperature of a beaker of hot water. The readings for the height difference H, right? So of course we're using theta is equal to theta is equal to H theta minus H0 all over. Right, so they said that ice point was minus 50. Right, steam point is 220. And the unknown temperature that's hot water is 105. All of this by 100. Right, so this is 155 divided by 270 by 100. Okay. Remember it's minus 50, yeah? Right, I got 57.4, right?
For what?
0.4, keep the gun figure. Right, 57.4 degrees Celsius.
After that.
Right, the part 2 missing, I can't find the year. So. The year is below. Oh wait, yes, look here. I think I just take all the part, be separate. Right. So the temperature on the thermodynamic scale may be obtained by using a constant volume gas thermometer. The thermodynamic temperature is given by, remember I showed you all that?
Yeah.
Remember I showed you all whose law is that again? Anyway, it's not a little bit different, but whose law is that? Pressure's law. Pressure law, right? Same thing, I just written a little bit. They just separate temperature and pressure. Right, but it is pressure law. Right, right. Here, T is the thermodynamic temperature, the triple point, P and T, pressure, the thermometer, and triple point respectively. The value of T is given as 273.16. Why is this particular number used? Why it is we use 273.16?
Isn't that triple point?
Right. That's why. So the triple point of water. The triple point of water is 273.16. That's why we use it, right? Atelia? Yeah. So the reason we use 273.16 is because that is a triple point of water. Right? And that's temperature T lower skip here, right? Alright. Now see what the flag is. Alright, now look back with our year, right? Then let's try one more. Okay, that's try part cleaner, please. Try that part there. Part B alone. So resistance thermometer is placed in a bath of a liquid at 0 degrees Celsius, and its resistance is found to be that value. At 100 degrees Celsius, the resistance is so much. The bath is cooled until the resistance is that. Find a new temperature in bath. Next, Marty.
Yeah, again.
Oh yeah, try that there. Right, I only have one answer from one line, yeah? That's Katrina. Nothing from Sarayan. In fact, never move Sarayan and steal it now. Part 1 and 2, done and finished. Part 1 and 2. 2 as well. So with the distance thermometer, they gave you R0, right? They gave you R0 as 3750 ohms. They gave you R100 at 215 ohms. And they gave you the unknown temperature, R theta, as 950. Okay, so all we have to do is 950 minus 3750 all over 215 minus 3750 by 100. How much you all got?
79.2.
Right. 79.2 degrees Celsius. But here's the problem, right? When they use a mercury and glass thermometer to find the same temperature, they got 76. Why? It can be that can be one of the things that we didn't draw parallax. What else?
Systematic error.
No.
Wait,
All right, can I speak up somewhere else? All right.
there can be something wrong with the thing.
Yeah, so thermometer. All right. You can get like a mark or two for us. Right? So one reason you said parallax, the next one could be systematic errors, environmental errors, yeah. Right? But here's what a next reason is. We're using two different thermometric properties, correct? One is resistance and one is the change in volume that's in mercury, right? So mercury expands and the resistance thermometer gives you resistance values. So one of the things is that different thermometric properties vary slightly with temperature. Right? So they don't vary the exact same way. So for example, a resistance thermometer graph might look like this. But if you do the mercury and glass thermometer, it might look a little different than the one underneath. Right? So they don't behave exactly the same. Okay, so make a note of that. Different thermometric properties. Different thermometric properties do not behave exactly the same. Do not behave exactly the same under the same temperature change. Under the same temperature change. There's a slight difference, right? Right, there's a small difference. Right? Everybody okay with that? Okay. Next thing you want to look at, take a look at two new quantities, right? Well, one new quantity, and I want to go over things that we did in Form 5. So remember, like heat capacity and latent heat, like,
Yeah.
right? It's also coming in this. All right? But I want to go over a new quantity called latent heat. All right. So there is this new quantity called internal energy. Real simple. Real simple, right? So think about it, right? Think about if you have a substance in a container. To raise the internal energy, all we have to do is to raise this kinetic and potential energy. That's it. Right? So the internal energy of a substance is the sum of its kinetic and potential. So if you want to summarize it, put a little formula. Internal energy is equal to the sum of the potential energy of the substance plus the kinetic energy. All right. So if you wanted to raise the internal energy, you can increase the potential or increase the kinetic. All right. How you can do that? Or you can increase the kinetic energy of a substance. Heat it. By heating it, you give the particles more energy and they move faster. Okay. So one way to increase kinetic energy is to heat it. What about potential? Right? It's internal, right? Or you can increase the potential energy internal. Make it more?
Yeah.
Which has more potential energy, a solid or liquid? Internal potential energy. A solid, right? Because of the bond, right? So how we can increase the potential energy of a substance? Freeze it. If you have a liquid, freeze it. Right? So what you can do is you can do work on the system, like compress it, right? And give it and allow the bonds to be stronger. So basically, when they say potential energy, is talking about bonding. Right? If you increase the internal bonds, you increase the potential energy. All right. So the internal energy U of a system is the sum of the kinetic and potential energy of the system. The internal energy of a system can be increased by doing work on the system and or putting heat energy into the system. Right? Those are two ways that we can increase the internal energy. Internal energy involves energy on a microscopic scale. For an ideal monoatomic gas, internal energy is strictly kinetic. What does that mean? What does this line here mean? They said for a monoatomic gas, that's a one atom gas, right? For one atom gas, the internal energy is strictly kinetic. What does that mean? And a potential, why? Right, so technically gases are gas particles are far apart, right? So there's little or no bonding between them. So therefore the potential is small. That's okay? Got it? Yeah. So therefore, the potential energy is small. So in an ideal case, gas particles only have kinetic energy, right? The internal is strictly kinetic. While for polyatomic gases, that's like gases that bonded to each other, right? They have rotational and vibrational kinetic energy as well. In liquids and solids, there is potential energy associated with intermolecular attractive force. If you look at this diagram shows you how gases and liquids and solids, what their internal energy is made up of. So for monoatomic gas, only have pink, right? Only have kinetic energy, right? For molecular gas that have those gas particles bonded together, they have vibrational, rotational, kinetic, and translational. And then for liquid or solid, they have both of them, right? They have the bonding plus the vibrate. So therefore, they have a mixture of vibrational and translational. Look at that. That's the concept of internal energy. Right? I don't think I have it in this handout here. We have to then go over kinetic energy, right? Sorry, we have to go over thermal quantities. Yeah. Right? So we're going to take a look at specific heat capacity and latent heat, right? Right? Hopefully we can remember them, right? Specific heat capacity, that was small c, right? Specific heat capacity, that's the first thing, right? That was the amount of energy required to change temperature of a particular mass. Remember that? Right? It was the amount of energy required right, to change temperature of a specific mass. Right? So anytime we undergoing temperature change, anytime a substance undergoing temperature change, then that temperature change indicates that the energy to create that temperature change is MC delta theta. All right? Anybody remember what big C? Right? Big C was heat capacity. That was the amount of energy required to do what? Change temperature. Nothing to do with mass, right? Just change temperature alone. Okay? And remember, big C was M by small c. Okay? Just in case you forgot, please remember that energy is equal to power by time, and power was equal to voltage by current by time. Okay? Sometimes you need to use one of them, right? Right? Energy required to change them. Right, so there are questions on this, but a little bit harder than the form five. Finish? You go. Right, so next thing that we need to get is latent heat, right? What is latent heat? Latent heat is the energy required to change what? Right? So it's the energy required to change phase, right? Well, that's general, right? So latent heat is the energy required to change phase. Of course, you have fusion and vaporization, right? So the energy required to change the phase of particular mass. That's the latent heat. Okay? So therefore, every time you undergo a phase change, the energy required is mLH. Okay? Right? Let's go to a small example. Let's say we had ice at minus 10 degrees to steam at 100 degrees. Let's just see if we could just set back up the graph. Thinking my mouse to do this now. Catch a graph to show how the ice goes to steam.
Yeah.
And then David, the list was the top most.
Right, don't forget out zero, right? Right, don't forget out zero. Here is zero, right? All right, so it starts at minus 10 degrees. When you heat it, it will reach to 0 degrees. Here is ice. Here is still ice. But as you heat it further, what will happen? It turns to water. Right? So it underwent a phase change here. If you heat it further, it becomes water at 100. If you heat it even further, it becomes steam at 100. Okay? So it underwent a temperature change, phase change, temperature change, phase change. That's okay? Right? And technically, well, the same power being delivered for it to reach all here, right? All right. So just to kind of refresh you on what you would have done in Form 5, right? Now to show you what the questions actually look like. Right? When you see it, it'll become challenging. Huh? You want to see it? Then when you see the point, it's not gone. I'll leave that one out and I'll be on good. Let's do this one together, right? What I will have to do is I'll have to use this first. All right, what you say? This here is the graph. I know it's kind of difficult.
Wait, what did I put away?
I know it's kind of difficult to see, right? But that's the graph of temperature with time of water being heated, right? You see the initial temperature of water? What's the initial temperature there? Tell me quick. 26, right? And what happened up here, Javed? What happened up here? It reached 100 and change state, right? Are you okay with that? All right, let us see if we can answer these little things here. The graph on figure 9, right, shows the variation of temperature with time for 1.1 kilograms of water heated in a kettle. Right, let's do my paper, write down the mass. The mass is 1.1 kilograms.
Of water.
Yeah, good, what? Yeah?
Yeah.
Right, here what I want you to do. Explain why the graph for the first 275 seconds is not a straight line. Why is it not a straight line? That's not a straight line, right?
What, 270?
275 seconds, that is. Yeah, cut out. Let's assume it's right here. That's 275, the underneath cut off, sorry.
Is a curve or?
No, I can't, it cannot bend and I wouldn't get it.
Wait, now say you think that was
No, not me. Come with the iPad.
interesting.
Right? That is a curve there. Right? Why is it that curve and not a straight line?
Impurities.
Huh? Impurities, nah, I don't like that.
Stop the loop.
Because it's measuring change in temperature over time. Why is it not a straight line?
Because of that.
Why temperature not steady?
Yeah, but
Huh? Think about every time we do a thermal lab, error is always what?
yeah,
Heat loss to the environment.
I said that.
So that, yeah, right? So because heat is being lost to the environment, there isn't that linear change with of temperature with time. Okay, so some heat is being lost, so it's not linear. Sometimes it's going linear, and then some lost to the environment, and then come back. Right, so it's not a perfectly linear relationship. All right, and the reason is because heat is being lost to the environment. Okay. All right, the power of the heating elements in the kettle is 1.6 kilowatts. Right, that power is 1.6 kilowatts. Power is 1.6 kilowatts. The time is 275 seconds. Right? Time during temperature change is 275 seconds. Right? I'm going to show it in the graphical too. Probably the way it's stable now. Right? Initial temperature was 26 degrees Celsius. Yeah? Ready? 26 degrees Celsius. Right. If the heat losses are ignored, right? So we assume it's a straight line. What value would the data give for the specific heat capacity of water? Go ahead, have fun. What value would the data give for the specific heat capacity of water? So use the right formulas and see if you can remember, we're focusing on this phase here, right? The straight line phase. Right? Time it takes 275 seconds to go from here to here. So the power of the heating element is 1.6.
Between the watts.
And G is what? Oh, right. See if we can find the value. So C on top of what you get. Remember, it underwent a temperature change. Get the next part up there. Do that too, right? How much bigger than that goes here today?
That man.
What color, black or purple?
It's white.
Yes.
It's white.
Mine is black.
No, white.
Now I said it's white.
That white, oh, white.
Yeah, but I blind on the
Yeah, I feel like black.
Well, oh yeah, we'll go down. Well, no, yeah. But yes, we class.
Yeah, that was the story.
Right, she just said that way.
It was the black. Yeah.
Now done?
Yes, 5, 4, 3, 5.
None to that.
About 26, and you want to put on. And it was on there.
Yeah,
Yeah, that flat line in the steel.
26,100.
I don't.
So of course, we're using E is equal to MC delta theta. And we know that C is equal to energy, power by time over. The power is 1.6 by 10 to the 3. What was the temperature? Oh, time was 275, right? What was the mass again?
1.1
kilograms, right? And the temperature change is 100 minus 27. Do I have to convert to Kelvin?
No, because we simply.
Yeah, just 26.
Yeah. How about?
26. It's 26.
Sorry.
Alright.
5405. Choose good each and good version.
Right, 5405. Can you get that, right? Joules per kilogram per degree Celsius, or you can write joules per kilogram. Anyone can. Right, they both be the same. Everybody okay with that?
It's like down there.
So I give you the hard one, yes. Right, the accepted value is 4200, suggest two ways to improve it. How we doing that? How we can improve this? How we get it? The value is 5405. It's supposed to be 4200. How we can fix it? Anybody? Jacob. We use my help. We out here. That's why I use the man. Pardon me? Do work on the. I know. Why was changing material? What was the problem at the beginning question? Heat being lost, right? So you want to reduce the heat being lost to the environment, right? So you want to reduce the heat being lost, so you can do it like when you do it in the lab, you do it like calorimeter. So you do it in a sealed environment, right? What else you can do? What else you can do? What else you can do earlier? Diane, what you can do? Do it more than once, and you could also shorten the time. Right? You can also shorten the time that you're running it for. Right? But of course, you can do the experiment more than once and yeah. Okay. You can also shorten the time. Right? You can even use a smaller mass. All right. One more to do. This one a little more challenging. All right, last one, and then I'll give you a break. Last one.
Why you want this?
Please. The graph on figure 7 refers to look at that. Going up with the graph on figure 7, although to 1 year, that is 2004. Oh, mighty fine.
You gonna read it?
Yeah, it's 4. Sorry. The graph on figure 7 refers to an experiment in which a crystalline material is heated at a constant rate, right? So it means applying the same power throughout. The material melts at 85 degrees Celsius. You're seeing that?
Yeah.
That melting, area horizontal. The material melts at 85 degrees Celsius and the liquid is heated to 110 degrees Celsius. Right? So then you keep heating the liquid phase. Right? Do you all see this solid phase?
Yeah.
Right? The solid phase is below the plateau and the liquid phase above, right? The specific heat capacity of the crystalline state is 40 kilograms per Kelvin.
Because like below 80.
Below 85. Yeah. The specific latent heat of fusion on a material. Find out. Right? So that's the horizontal part, right? Go ahead. It's a little tricky, plenty little marks, right? It's not difficult, but that's a marks to kind of move around with. Right on everything I have, then figure it out.
Discuss around like so I
Right? The hint here till here is that the same power being delivered. Same energy. Same power, sorry, I shouldn't say energy. Same power being delivered. Right? That's the hint. Same power being delivered. Right? So you see, like, if I had to put the question out, right? I would have recognized that number 1, I want to get latent heat of fusion. So I need energy over mass. Correct? I don't have energy, I don't have mass. Right? Next, turn the page, but next. What's it gonna do? Turn the page. But I recognize that there's a lot of information during the crystalline state,
Yeah.
right? During the crystalline state, we use E is equal to MC delta theta, right?
But you're not even able to get E or M. Okay.
Right, so let's just see what will happen. That's why I said this question, yes, physics, but a little more maths as well, right? So I wanted to show you something, right?
It's so cool.
We know that energy is power multiplied by time, correct?
Yeah.
We don't know the mass, but then we know C. C is 430, right? What is temperature change that underwent during the crystalline state?
250. No, 85.
85. You're saying that from 0 to 85? Yeah? How long did it take, I tell you? How long did it take during the crystalline state? 50 seconds. So it might be possible for us to find P, right? P is equal to M by 430 by 85 all over 50. You'll see that? And the same power being delivered here.
Yeah.
See if you can put them together. See if you can put them together and find Ellen. Right? And remember, that's the way you answer any question. You have to use the information given to help you find, right, what you need. Okay, Faith? But 430 by 85 divided by
731.
731, right? So P is 731 M. So you may recognize that energy is power by time, right? The same energy here is power by time. So power is 731 M by how long did it take to melt?
50.
15 seconds. All over M.
Then MP first.
M will cross. Right? You're not going to just magically see that. You have to learn to manipulate the quantities it gave you. Right? So you have to work with this part here first. The M will cancel and you'll get 731 by 50. 10965 joules per kilogram. Joules per kilogram. Right, you have one last part. The specific heat capacity during the liquid phase. Hopefully it shouldn't be that hard. So you recognize that we didn't even need to find them, right? Selena, follow? Follow? I said, this is what you need to learn to do, right? Put those quantities together. Right? Use the known to find the unknown. Is that true? Double them together. Huh? Are you finished? Take your time. I thought we said it's the same power, right? Same power being delivered. The power constant. What shall I get?
1608.1608.
Okay. So C is equal to power by time all over m delta theta. So the power was 731 by m. The time is 5:55. The time is 55 seconds. M temperature change is
25.
25. M will cancel. M will cancel and you will get 731 by 55 over 25. Right, I got 106.8. 106.8, that would be what? Joules
Kilogram per
per
Kelvin.
kilogram per Kelvin, right?
Celsius.
It's okay to put Celsius.
I can tell.
Right, last one.
What?
Last one.
Yeah. This one you have one?
Alright, so yeah. Oh wait, no, you have a multiple choice.
So, yeah, we start pure, right?
Yeah.
Yeah.
Wait, why is that not?
Yeah.
Alright, let's keep them, multiple choice, not sure.